Hello. So, two topics I thought would be important to review for the AP exam from Module 6 are Newton's law of heating and cooling and growth and decay. So, first up is Newton's law. Here are three important definitions to understand the law. So, first of all, the law itself is a differential equation that shows that the rate at which an object heats or cools is proportional to the difference between the object's temperature and the temperature of its surrounding environment. To find this, we have to use the initial value, which is the starting value, and we use this to help solve for a particular solution rather than a general solution to the differential equation. And then finally, the constant of integration, which is k, is added when integrating, and it determines which of a family of antiderivatives the particular solution belongs to. Okay, so here is a general formula for the differential equation when we're finding heating and cooling. And it's just dy over dt equals k times y minus b. Notice that if k is positive, it'll be decreasing, and if k is negative, it'll be increasing, and then if it's negative, it'll be decreasing. And b is a fixed constant. K is the constant of proportionality. And then we can solve this differential equation to find the general form y equals a times e to the kt plus b. And then here's all of what the variables stand for. And obviously the numbers within these will change from problem to problem, but these are both two general forms that will work with every heating and cooling problem. So an example problem that I found helpful for Newton's law is the milkshake problem. So it tells us that basically I summarized it in these three pairs to show what the problem gives us initially. So the starting temperature of the milkshake is 28 degrees Fahrenheit. After 10 minutes, it's 35. It is heated up to 35 degrees in a 70-degree car. And after 20 minutes, we're trying to find what the temperature's at. So we start with the differential equation, which you'll notice has the exact same form as back here, except this time we know what b is, the fixed constant, which is 70, because the car that the milkshake is 70 degrees. And then we can just solve for the differential equation like any other differential equation and find the general form, which will eventually help tell us the temperature, or help tell us the time for the given temperature. So we have T equals A times E to the KT plus 70. Okay, so the next step is to plug in our initial value that we're given. Because we know that the capital T is temperature and the lowercase t is time, we're able to plug in 28 for 28 degrees Fahrenheit at 0 minutes. And then e to the 0 is 1, anything to the 0 is 1. So we just have to subtract 70. 28 minus 70 is negative 42. So now we know two variables from the general formula for heating and cooling. And then the next step is to plug in the second piece of information we're given, which is that milkshake is 35 degrees at 10 minutes. So we plug this in and then just use algebra to solve, and we get that, and this is how we find the constant of integration. So we find that k equals ln of 5 over 6 over 10, which if we have a calculator we can find as negative 0.018. And so at this point we're able to answer the first part of the question, which says to write a differential equation modeling the situation. So this is the differential equation, this is the differential equation after we've solved it. So now we're able to use it to estimate temperature of milkshake 20 minutes after purchase. So all we have to do now is plug in 20 for the time and find what big T equals, which will be the temperature, which is about 40.833 degrees Fahrenheit. So right here I've just made a quick little summary of these general steps so we can apply them to any heating and cooling problem. So first we have to solve the differential equation. Then we find A by plugging in the initial condition, which was the temperature at 0 minutes. And then we found K by plugging in the second coordinate that was given to us in the problem. And then finally we solve for Y at the given X. Or you could solve for X at the Y or any other variable. So the next topic I covered was growth and decay. Two important definitions for growth and decay are particular solution, which is the solution to a differential equation given the initial condition, and then the general solution, which is an entire family of functions that differentiate to a given differential equation. So here's just some notes to understand about growth and decay problems. So these are just sort of examples, but if we look at these three differential equations, we notice that each of them solve to sort of a similar form. So P equals A times e to the 0.02t, A times e to the 4t, A times e to the 1/3 t. So what we notice is that if the differential equation is written in the form dy over dt equals k times y, it can always be solved to find y equals a times e to the kt. And this is significant because we can then, if we're given initial conditions, we can plug them in and find solutions for all these. So we can find things like growth rate or the size of a population after a certain amount of time, how long it will take for something to increase by a certain amount, decrease, double, triple. And this can be really helpful in things like finance, medicine, population growth, like in different species. So the example that I have here is of a population of a city. It says that the population of a city grows at a rate proportional to its population. If the annual growth rate is 4%, how long will it take for the city's population to double? So first we write our differential equation, and we know that our constant is 0.04 because it grows at 4% annually. And then we can solve this to get P equals A times e to the 0.04t, and we don't really have to go through all the steps to solve for P. We can just use this general form and plug in the variables. And then this one's sort of unique because it doesn't give us a specific y to plug in, but all we know is that we're finding the time it takes to double, so we can put A as 1 and P as 2, and then solve for lowercase t, which is the time in years. And then that's ln of 2 over 0.04. If we have a calculator, we know that's 17.329 years, rounded to the nearest 3 decimal places. And that's it, the end.